In this unit, we're going to be talking about chemical kinetics. And chemical kinetics is basically a study of reaction rates. So it's how quickly reactions proceed. That is, so the rate of which the reactants are expended or used up, and that products are formed. And so remember that in math when we talk about this idea of a rate, we're talking about how quickly something happens. A speed is a rate of distance. You cover this distance in this time. In this case, we're looking at a reaction rate. So we can think of it like this: a reaction that has a high reaction rate is one that reacts very quickly, whereas one with a low reaction rate reacts slowly. So we talk about like a high reaction rate example would be something like combustion of hydrogen gas. This picture that we have over here that shows a very, very quick reaction is that hydrogen ends up being reacted extremely, extremely quickly. A low reaction rate reaction could be something like rusting of iron. You take a piece of iron, you leave it out. The iron does combine with the oxygen in the air to form an iron oxide, but that reaction takes a very, very long time. That piece of iron will take a very, very long time for it to completely rust through. And so that's sort of what we mean when we talk about reaction rate. High reaction rate means the reaction happens quickly. Low reaction rate means it happens slowly. Now, understanding how these reaction rates work allow us to predict several things. One is obviously, how long the reaction will take. Obviously, we can figure that out if we know the rate. But another one that comes out is the rate at which the energy is absorbed or released. If you wanted to have something that's going to release a lot of energy in a very short time, you would want it to have a very high reaction rate if it's coming from a chemical reaction. It also lets us figure out what the concentration of the reactants or the products are after a certain time, so that you say, I want this to produce a certain amount of a compound after a certain amount of time, and it would let you figure that out. Now, oftentimes we as a practical matter want to be able to adjust reactions to go at higher rates, like we talked about, explosions. You want that to be a very rapid reaction. You want to have a very high reaction rate. If it doesn't, then it would be not a very good explosion. You might want to have it be a lower rate. Slowing down reactions in biological decay, it mentions right here, is that so if you don't want food to spoil, that's food spoilage happens through chemical reactions, and so we want that to be a very slow reaction. And then sometimes tuning a reaction to have just the right rate. A good example of this is we do this with medicines. If you have too fast of a reaction when you take a certain drug, that can be deadly. If it's too slow of a reaction, it could be ineffective. And so we sort of just want to fine tune those reactions so that they have exactly the right rate that we want. There are four major factors that are going to determine what the rate of a reaction is. The first one's sort of our catch-all. It's basically the nature of the reactants. That will cover things like phase, solid, liquid, gas, the size of the particles, the type of bonding, ionization energy if they're metals. So that's our first category here. The next three are probably the big ones right in here. Concentration of the reactants, the temperature, and the use of a catalyst, which we'll talk about later. So let's jump into the nature of the reactants first. So first thing, just a basic idea on what has to happen to react. If I have a reaction between two particles, between two substances, the particles have to collide. They have to run into each other. If two particles just sort of zip by each other, whoops, so that those two particles, basically one goes this way and one is down here, and they never hit, then there's no way they can possibly react. So they have to collide with each other. Okay, and so the phase, whether it's a solid or a liquid or a gas or whether it's an aqueous solution, affects very strongly how easily particles can come in contact with each other. And so because of that, it affects the rate of the reaction. Examples of this could be solids. In solids, the particles are basically joined by intermolecular forces together. The particles do move, but they don't sort of change position. They tend to stay in place. In this picture that we have down here is that, we have this little particle right there, and that particle tends to stay in between those other particles that are here. It doesn't really go from one place to another. It doesn't flow. And so because solids are held very tightly by their intermolecular forces, and the particles just don't have enough energy to break free of those intermolecular forces. But the end result of this is that substances in solid form can only react along their surfaces. So down here we have this sort of picture of this chunk of some green material down here, and we have these red hydrogen atoms that want to bond, and so to collide with these, they're able to collide with the atoms that are on the surface, but they can't bond with any of the atoms that are in the middle because they're just not available. And so solids tend to have lower reaction rates than other phases. Now, we can adjust this because if you do have a solid and you want to increase the reaction rate, you can do this by breaking the solid up into smaller pieces, as it sort of shows on this side. By breaking them up into smaller pieces, now there are more of these green substance atoms or green substance molecules that are available. Is there only a very small number that are sort of stuck in the middle that are unavailable because we've broken it up? And so the fact is that oftentimes if we want to increase a reaction rate, we can break a solid up into smaller pieces like this. And if you really wanted to increase the reaction rate, if you could dissolve this substance, then once it's an aqueous solution, is the individual particles of the solid are now even more spread out. They're even more available to be collided with and to be reacted with. This is one of the reasons why for a lot of medicines is that we put them into capsules. If you have a capsule and you open it up, you'll see there's a powder inside. And so one of the reasons why they do that is by breaking up into smaller pieces, it allows them to be more readily absorbed. It allows that sort of reaction to take place at a higher rate. And so as a result, you end up with a higher reaction rate. So you want to slow the reaction rate down, use bigger chunks. You want to speed it up, try to take that solid and break it up into smaller pieces. Now, if we have liquids or gases or aqueous solutions, these are going to tend to have higher reaction rates because as they're all fluids, they can mix with each other. And so the particles are more likely to come into contact because there are none that are completely isolated in the way that they are with a large chunk of a solid. Now, this is only true if they mix well, right? They have to be able to easily mix. If they separate out, like, we talk about oil and water, or any time that you try to put together two liquids that, let's say, one's a polar liquid and one's a non-polar liquid. So they don't tend to want to react here. If they have different densities and they separate out so that, you have whatever your substance is, and you have, like, substance A that floats on top and substance B that ends up being down on the bottom, is that if that happens, then you're not going to get a whole lot of mixing because they'd only be able to collide right at the surface right there, but they wouldn't be able to mix fully. If you're able to get A and B to completely mix entirely in this, then you're going to see a much higher reaction rate that's going on here. So anything we can do to have these fluids mix better is going to have a higher reaction rate. Now, so let's suppose, what if you had a gas in a liquid? Well, if you had a gas in a liquid, one of the problems you could run into is that your liquid substance is going to be down here. Your gaseous substance is up here. The gas particles are generally only going to hit the liquid at the surface unless you did something like bubble the gas through, which is sometimes a way that you can get a reaction to happen here. You'd be better off if they were both gases, because if they're both gases, then inside whatever container this is, all the little particles are all sort of flying around here. And so they'll run into each other as they move around because there's nothing that's really keeping them from just hitting any particle potentially. So solids tend to react the slowest. Liquids tend to react a little bit faster than solids if they mix well. Gases react even faster if they mix well. Aqueous solutions react sort of similar to liquids in terms of their reaction rate. So anything causing a mix, anything causes make the particles more likely to come into contact with each other will tend to increase that reaction rate. All right, so next thing, as far as nature of the reactants goes, the types of bonds. Substances that are ionically bonded are typically more likely to have a higher reaction rate than those with covalent bonds. And so here's the reason why. Imagine we have an aqueous solution of like, we're actually deciding aqueous. Let's just say we have two solid substances, is that we have an ionic substance, let's say sodium chloride. And so remember that this wants to form, for sodium chloride, it's going to end up forming this crystal lattice where we end up with all the negatives surround the positives, and we have the positive sodium ions that are going out here, and it just makes these patterns forever and ever, well, indefinitely, not forever, but indefinitely until the edge of the substance comes. Now, if I have some new ion that wants to react, like a magnesium 2 plus is going to come up here. Really all this chlorine that's right here has to do is this just going to jump over. It doesn't really have to do much to be able to do that because it's just electrostatically attracted. The negative chlorine is attracted to the positive sodium. I introduce a new positive magnesium, it just jumps right over. It doesn't take a whole lot for it to be able to jump from one to the other right there. So ionic bonds tend to have higher reaction rates, or substances that have reactants with ionic bonds have higher reaction rates than those covalent, because if I had a covalent bond, like let's say that I had something like, I don't know, carbon dioxide. Oops. So my carbon dioxide right here has a double bond with oxygen right here. You've got to be able to break those bonds to be able to get that reaction to happen. If the carbon was going to go and, I don't know, react with like a fluorine or something like this. And so, they're sharing those electrons. It's a lot harder to break those bonds quickly than it is with the ionic bonds there. And so you tend to see higher reaction rates with ionic substances than covalent substances. Another thing, we talked about that carbon dioxide is a double bond. That makes a difference. The strength of bond. Substances that have strong bonds tend to react with lower rates than substances with weak bonds. We talk about, say, this doesn't happen, but if you had an oxygen pair that had a single bond between them, that'd be a whole lot easier to break than an oxygen pair with a double bond between them. Because, with a double bond, you've got two overlapping orbitals that are both sharing electrons, and you've got to break both of those to be able to get the reaction to happen. It's much easier to break the single bond here. So weaker bonds, you tend to have higher reaction rates. Stronger bonds, you tend to have lower reaction rates. Okay? Last one we have here, metals. Now, metals, remember, hold on to electrons loosely. They tend to have low ionization energies, but some metals have lower ionization energies than others. If you have a low ionization energy, it means that metal doesn't hold on to its electron very tightly, which means it's very easy for that electron to leave, and so it tends to leave more quickly. And so if you had something that had a metal with a very high let's say we had rubidium, a very low ionization energy like rubidium holds on electrons very loosely. It's going to react typically quicker than something like aluminum, which holds on to its electrons much tighter. And so low ionization energies tends to mean high reaction rates. High ionization energies for metals tends to indicate that you have a lower reaction rate. Now, what about our other factors here? Well, to understand those other three, which are temperature, concentration, and catalyst, we're going to need to talk a little bit about collision theory. And we've already mentioned a little bit, that we have to have particles collide in order for reactions to happen. But collision theory goes beyond that. It doesn't just say they have to collide, they also have to have enough energy to be able to break the bonds of the original reactants. If they collide and they have a very, very small energy, they tend to just bounce off of each other. So, I have, molecule A, molecule B, they're going to run into each other. If they hit slowly, they'll just bounce back off. Nothing happens. There's no reaction. But on the other hand, if they hit very quickly, then they may have enough energy to be able to break those bonds. And we call that minimum energy that's needed for the reaction to occur the activation energy. Okay, so this little diagram that we have on the right here sort of shows this. In this case, we're reacting hydrogen and chlorine gas right here to form hydrochloric acid. And so in order for this to happen is that that hydrogen molecule has to hit that chlorine molecule, and it's sort of showing that's happening right here. But if they hit each other too slow, basically it's almost like they have enough energy to get up to this point right here, but then that's all they can do, and so they'll just come back down, and they end up staying as hydrogen, and they end up staying as chlorine gas. But if we were to give those enough energy to come all the way up here, they'd be able to make it up over this hump and end up in those products form. And the reason why we have one layer level that's higher than the other is this deals with some of our thermochemistry stuff where we talked about that the original energy before and after, and whether or not this is an endothermic or exothermic reaction. That's going to matter as far as why one side is higher than the other energy-wise. But for this to happen, you have to be able to get up over this activation energy hump. They have to have this minimum energy to be able to react. Now, in reality, when you have, let's say, this hydrogen gas and this chlorine gas, they have a certain temperature, they have a certain amount of energy here. In reality, there's a big distribution of those energies. If you actually graphed it, it would look a little bit like this, and so you'd see that there's an average, a sort of an average energy that they have here, and so that anything above that has more energy, anything below it has less energy, and so if you have an activation energy that tends to be like somewhat up in here, because this is energy on this axis right here. This is like number of particles on this axis. Is that only those that are above that activation energy be able to make it across. So there are even at low temperatures that would be able to make it over the activation energy hump, but not many. Okay, but on the other hand, if your activation energy was farther down, it was down here, then everything that's above this, all those particles would be able to make it over, and only that little tiny sliver of particles that are below that activation energy wouldn't be able to make it. But the key is recognizing this, is that what we mean by this is that the particles have to have enough energy when they collide to be able to break the bonds, and that energy we call the activation energy. Now, the higher the activation energy is, the more kinetic energy the reacting particles will need to react. So if you have a very high activation energy like this one right here, where that's a relatively high one compared with reaction 2 down here, is that those particles must be going extremely quickly to be able to have enough energy to get up over that hump. They must be going extremely quickly, because it's not a physical hump, this is just an energy diagram. They must be going extremely quickly to be able to break the bonds, because what's showing it here is this activation energy is high. It takes a lot of energy to break those bonds, so they have to hit really, really fast. And so if the reacting particles collide with less than the activation energy, they just bounce off. But if they have more kinetic energy than the activation energy, the reaction proceeds. It's going to go ahead and form its products down here. And so, if you had some situation where, let's say that your particles had an energy that's like this, then they would not be able to react in reaction 1, but they would just barely be able to react in reaction 2, because that for reaction 1 it takes a lot more energy for them to hit to be able to break the bonds. Reaction 2 doesn't take as much energy, and so that's why that activation energy is lower. And so that reaction only proceeds if they have enough kinetic energy. Now, what this ends up meaning is that they need to be able to go quickly to be able to react quickly. So let's look at concentration. We said in order for the particles to react, they have to collide. Reaction rates are higher when the concentration of reactants is higher. So in situation number 1 over here, there's a very small concentration of red particles, and so there are not going to be very many collisions between red and blue. Most of these blues are just going to run to other blues. They're not going to hit reds, and so because there's a low concentration, there are very few collisions. In example number 2, there are a lot more reds. There's a higher concentration of red particles, and since there's a higher concentration, they are more likely to hit. And so higher concentrations, reacting particles are more likely to collide, so reactions speed up. So higher concentrations, higher reaction rates. Lower concentrations, lower reaction rates, because they have to collide, and if they're higher concentrations, they're more likely to collide. Now, temperature. So we said that in order for them to be able to get over the activation energy, they have to have enough energy. We talked about hitting quickly enough, and that's related to temperature. So the rule is this: reaction rates are higher when the temperature of the reactants is higher. The hotter you make your reaction, typically the faster that reaction is going to go, all things being equal. So 2 reasons. 1, at higher temperatures, reactive particles move faster. So number 1, first reason why that makes reaction rates higher. Faster moving particles will collide more often. They're moving slowly, they'll collide, but they may not collide often. They're fast, they go ding, 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 ding. They just hit a bunch of things right in there. Second reason, this gets to our activation energy. Faster moving particles are more likely to have an energy greater than the activation energy, and so they're more likely to break the new bonds. They break the original bonds and form the new bonds here. Okay, so higher temperatures means faster reaction rate. And in fact, the reaction rate is extremely sensitive to temperature. We can sort of say as a rule of thumb, just as sort of a general rule we can apply, each increase of about 10 degrees Celsius results in a rough doubling of the reaction rate. So if you have something that's at room temperature, somewhere in the neighborhood of about 20 degrees Celsius, and then you increase that temperature to 30 degrees Celsius, you've basically probably doubled that reaction rate. You increase it from 20 to 40, it's 4 times larger. 20 to 50, it's 8 times higher reaction rate. Very, very sensitive reaction rates are to temperature. Okay, so last one out of these is catalysts. So a catalyst, okay, is a substance that participates in a chemical reaction but is not used up in that reaction. So it's involved, but it doesn't get used up. So it's not a reactant. Reactants get used up. If you have hydrogen gas reacting with oxygen gas to make water, is that when you're done with that reaction, you've lost some hydrogen and you've lost some oxygen gas. They're used up. But a catalyst is not, even though it participates. An analogy we could sort of use is this. If you want to make a peanut butter and jelly sandwich, you need 3 reactants, three ingredients. You need bread, you need peanut butter, and you need jelly. And you only need those 3 to be able to react bread and peanut butter and jelly to make your product peanut butter and jelly sandwich. But you can do it a lot faster if you include a catalyst, a knife. If you can make a peanut butter and jelly sandwich without a knife, it'll work. It's just messy and it's slow. But if you include the knife, it'll speed up that process. And when you're done, you still have a knife. The knife participates in the creation of a peanut butter and jelly sandwich, but it's not used up. It's not like that every time you make a PB&J, you've got to get a new knife. Is that you can use that knife over and over and over again to make many, many, many sandwiches. And the same thing is true for catalyst, is that in certain reactions, you can add a catalyst to it. It participates in the reaction, but it's not used up. And so the reaction happens, the catalyst remains there. It can be used in additional reactions later on. An example of this is there's platinum that's in your car's exhaust system as part of the catalytic converter that's involved with trying to participate in the reaction to remove some of the pollutants from your car's exhaust, but it's not used up. And so it stays in there and you don't have to replenish it. Now, here's how catalysts work in terms of reaction rate. They change what we call the reaction pathway. And so the reaction pathway is basically the intermediate steps that go on during the reaction. And we haven't really focused on this too much, but oftentimes in reactions, we sort of treated them like they're one step, like that H2 plus O2 yields H2O, and that just happens just like bam, just one step right there. In reality, most reactions tend to take multiple steps, is that, the H2 has to come apart, then the O2 comes apart, and maybe an H goes with an O, and then the other H comes in later on, something along those lines. But those steps that it goes through, those intermediate steps in the process of doing the reaction, catalysts change. And a well-chosen catalyst will change those steps so that the activation energy ends up lower than the original steps. So in the picture we have at the bottom, we have what's originally a reaction between substances X and Y to produce product Z. And so originally this is a one-step reaction. That's what is showing on the black graph right here. So no catalyst is added. The activation energy ends up being way up here because it's a one-step reaction, and it just happens to be what that activation energy is for that reaction. Now, by adding the catalyst, it turns that one-step reaction into a 4-step reaction. So we have step 1, step 2, step 3, and step 4. But what you notice about this is that every individual step in this 4-step reaction ends up being a lower overall energy than the original activation energy. And so as a result, the activation energy is lower. Since the activation energy is lower, the particles don't have to be going as fast to be able to collide. And so if I have particles that are let's say that my particles are going fast enough so that they're at this energy right here. If they had that much energy to start with, they would be able to react with that no catalyst situation. And they would be able to react with the red catalyst situation, but more of them would be able to react at the catalyst because the activation energy is lower. And so even at where the average is at this point right here, there's still some particles that are not quite able to get over that original hump here, but they are the new one with the catalyst right there. You can almost think about this in terms of that multiple steps can end up requiring less energy than one step. It's sort of like getting flights. If you're in Des Moines and you want to go to Los Angeles, is that it's not always the case that the cheapest flight is a one-way flight. Sometimes you've got to fly from Des Moines to Atlanta and then Atlanta to Los Angeles, and that path that ends up being that's 200 and that's 100, but from Des Moines it's 400 on a straight route here, is that by taking multiple steps you can oftentimes save money. And the same way, by taking multiple steps, if you do it right, by adding a catalyst, you can end up with a lower activation energy, make it easier for the particles to get over that activation energy hump, and so therefore more particles react, and so therefore the reaction rate ends up being higher. And that's really what we're talking about here. New activation energy is lower, more particles have enough energy to react when they collide, and this leads to a higher reaction rate.